So in this video, we're going to talk about the properties for taking the derivative of an inverse function. And where we're really headed with this is to eventually take the derivative of inverse trig functions, as well as taking derivatives of logarithms, since logarithms are the inverse of exponential functions. So in this video in particular, we're going to go through the notation and we'll basically go through a proof of why this works. And then we'll move into inverse trig functions, where we'll get a bunch of different rules that we need to follow when taking the derivatives. But all of those rules that we're getting comes from this exact scenario here. So let's go ahead and talk through this, and we'll see how this kind of operates. So let's say we have an original function f of x. And what we're going to do in terms of notation is use g of x to represent our inverse function. So again, our notation here with that -1 up there, that -1 is not a numerical value, it's just symbolically representing the inverse of f of x. And as a reminder, those inverse functions, it's switching how our x's and y's operate. So we're using g of x to represent the inverse of f of x. So if we want to know the derivative of our inverse function, so that's our g prime of x, is this derivative of the inverse of f of x, we can find it by using this calculation. So what this is we have 1 in the numerator, and then in the denominator, what this is. So again, on the inside g of x, so that's our inverse function. And then what we're doing is we're plugging into the derivative of our original function. So just in words, it's the inverse of f plugged into the derivative of f. I'll say it, it's a weird one. It's a weird one, and again, we're not going to see this specific setup terribly often, but it is the basis for all the formulas that we're going to get out. So what we're going to do is go through one scenario and see how this works. Real quickly, and you're welcome to skip ahead, I can show you a proof of why this works. It's a really short but sweet proof in case you're curious. And it's a good review of the basis for inverse functions. So with inverse functions, they kind of undo each other. So if we set it up where we're taking our function f and we plug in our inverse function, this has the property that if we take the inverse and plug it into the original function, all we should get out is just x. So let's say we take the derivative of both sides here. And derivative of the right-hand side. So on the left-hand side, we'd have chain rule here. So what we would have is our outside function. So just regular f would be our outside function. Inside function would be our inverse function. So we want to take the derivative of the outside, so f prime, and we keep the inside the same. And then we multiply by the derivative of the inside. Now, this does have some interesting notation, and it's completely why we're throwing in this g of x down here. So what this would look like is we have our inverse, and we're taking the derivative of our inverse function. So it just uses some extra parentheses, but that's what we're using to represent g of x over there. And then derivative of x is just 1. But the idea is that we're interested in solving for, this is the derivative of our inverse function. So if we want to find this derivative of our inverse function, we can just divide away everything on the left there. So that's where we end up with 1 divided by f prime of our inverse function. So that's exactly what we're using down here. But I also want to show this just to use that consistent F notation, so you can see how it's all kind of tying together, but it's a lot of notation, but that's where the proof comes from. Okay, so let's show how this works. And again, with this, like if I give you a function g of x equals x plus 2 over x and say to take the derivative, we would just use the quotient rule and be done with it. But what we're going to do here is just a little bit of proof to show that this works using our inverse function. So what we're going to do is actually have g of x, so this represents our inverse of f of x, meaning we're going to bring in f of x and use that to solve pieces here. But just for the sake of it, off to the side here, let's start with what g of x is x plus 2 over x. If I want to take the derivative of that, let's see, we'll go quotient rule, so low d high minus high d low all over low low x squared. And if we just simplify that down, what we'll have an x minus 2, so that'll be a negative 2 over x squared. So if we're interested in the derivative there, done, all good to go. But for the sake of this exercise, let's say if I know this x plus 2 over x is operating as an inverse to some original function, we're curious what that original function is. So first thing I would do is find our original function. So let's say I want to find f of x. So what we'll do is just take the inverse of this inverse function. So again, we could think of it as y equals x plus 2 over x. And then what we do is to find the inverse, we switch our x's and y's. And then I'm going to solve for y. So multiply both sides by y. Subtract y so that I get everything with y on one side of the equation so that we can factor. And then divide away so that we get y all alone, 2 over x minus 1. And what this represents here is that this would be our original f of x function. So we know what f of x is, we know what the inverse function is. So what we can do is, for my notation of where we want to end up, we know what's plugged in here, g of x, we have that right here. What I need to plug it into is the derivative of f of x, so we just found f of x. So now I want to take the derivative. There would be a few different ways to go about this one. What method do I want to use? Let's just go quotient rule. So low d high minus high d low all over low low. So we have, that'll be multiplied by 0, so that'll just kind of wipe out. So a negative 2 times 1 over x minus 1 squared. Okay, so we needed to know f of x so that we could get here to the derivative. So now let's go to the step where we plug in to our formula up here. If I want to take the derivative of this function, x plus 2 over x, which would absolutely be so much easier with just the quotient rule, but again, this is just an exercise to show that it all matches up. We could do this using this inverse property. What I'm going to do is 1 over, and then I want to take the derivative function and plug in my inverse function. So in the denominator here, I'm going to take that take that derivative, negative 2 over, and I'm going to go x minus 1 squared, but instead of plugging in x there, we're going to plug in our function g of x. And now we do some algebra. Let's rearrange things so that it's not complex anymore. So you could think of this as like dividing fractions. So we're going to do a keep, change, flip. So it's 1 times the flip of that denominator. All to say we'll end up with x plus 2 over x minus 1 all squared over negative 2. Inside the parentheses there, instead of a minus 1, I'm going to think of that as x over x, so I can combine those together. So it will have x plus 2 minus x all over x being squared, which would be a 2 over x squared, so 4 over x squared divided by negative 2, which is 4 over negative 2 x squared, which is a negative 2 over x squared. All of that work to end up right where we knew we should land at the beginning there. So, much longer process, but it just proves that if we think of inverses, what you can do is take that original function and use that derivative, and that will be your outside function for plugging in your inverse function. So we layer things, simplify, and that will get you to the derivative of that inverse function. But again, this process isn't what we're going to use for standard functions. But it's the basis for what we do next. So all that to say, let's go on to see what happens if we try to take the derivative of inverse sine of x. And for this one, it's nicer of if this is our inverse of f of x, then we know our original function would just be sine of x. So if I want to understand the derivative of inverse sine of x, so if I want to take g prime of x, using our rule from up above, we'll go 1 over, and then I need my derivative function. So if f of x is sine of x, then f prime of x is cosine of x. So we're going to take our derivative function, cosine of x, and then what we plug in is our inverse function, which will be the inverse sine of x. And then what we want to do is simplify. We want to simplify that denominator. And that's where I started to draw out this unit circle here, because that will help us with our steps. So with our inverse functions, it's important to remember, so if we're taking sine, we're a regular function, so like sine of an input of x, that's where we plug in an angle measurement and get out a y coordinate. With our inverse function, it's that we plug in the coordinate and get out the angle. So all of this is going to relate to an angle measurement, and what we're plugging in relates to a y coordinate. So let's say I have my unit circle down here. And we're going to go with we're landing in some spot in the first quadrant. So for some angle measurement, and the notation's not going to be super fun here, but we're going to use this variable x to represent our y coordinate. So wherever that angle's landing, we have x for this side length here. And then we know 1 is our radius. And then if I want the other side length, which would be relating to our x coordinate, so what we could do is solve for that side length using the Pythagorean theorem. So x squared plus y squared equals 1. So if I wanted to solve for that side length there, go 1 minus x squared, square root of both sides. Then we should have plus or minus, but we're going to stick to positive land here. So we're getting a root 1 minus x squared for that side length. So this angle measurement, if we have a y coordinate of x, then the x coordinate would be the square root 1 minus x squared, and then a value of x over there. So simplifying this function, we have 1 over, and then this inverse sine of this y-coordinate is relating to that angle measurement. So I could go is cosine of, and then we're saying we're at this angle, whatever it is. And if we're taking cosine of that angle, well, cosine relates to our x-coordinate. So with that, we're going to have 1 over square root 1 minus x squared. And that right there is going to be our rule for taking the derivative of our inverse of sine of x. Oh, what a mouthful. So when we get to our next page here, we're going to start with that first rule here of taking the derivative of that inverse function relates to 1 over the square root of 1 minus x squared. And it all comes from that rule for taking the derivative of inverses with this plugging in and layering of the functions. But instead of proving this for every single inverse function, we're just going to get our rules and start applying them. But this is where it all comes from.